This was a talk that was given on October the 11th at a logic discussion group at the University of Leeds. So I'm going to motivate proof complexity a little bit by talking about complexity classes. So we're going to talk about this framework here. So we've got an input, we've got an algorithm, and we've got an output. We can define measures on these three things. So for input and output, we're talking about size. So this will be size maybe in terms of how many characters you need. So those characters could be binary, which is the most usual case, or it could be like size in terms of like numerical size, right? But normally we're talking about sort of size in binary. And I think that's probably the most important case. And that's the case we're going to be using going forward. An algorithm, it also has time. So if we look at, in computer science, we have this model of how much time an algorithm needs to take. And this is usually in terms of how many steps our machine needs to do. And when we're talking about time in general for an algorithm, right, it depends on the input, right? But we want to sort of factor that out. So we look at time in terms of average time, or we could look at like worst case time, right? So we're going to use this framework to define some complexity classes. So we're going to look at first at the class P. So P is the class of all languages that can be decided in polynomial time. So what does that mean? Well, our language is going to be our input. So we're going to take some word from our language or some theorem from our language, and we're going to input it into our algorithm. Okay, and the idea is we're going to get an output of size 1. So this is going to be a binary character, which is going to tell us whether it's in the language or it's not in the language. So our input could just be any string, and we're just looking for strings that belong in our language. And what our algorithm does is it checks that. It returns 1 whenever it's in our language. So the important thing about it being in the class P is that our algorithm runs in worst case time polynomial in the size of our input. So here I've used this notation here to denote polynomial. All it means is that we've got it's time n to the power of something, and this something is a constant. Okay, because if it was something bigger than a constant, we might think of it growing exponentially in the case of it being linear rather than constant, for example. Okay, so we defined this class P. So this is a class of problems that computer scientists like to think are easy problems so sort of like languages that are feasibly checkable or feasibly decidable. The other class that is quite famous is the class NP. So NP is traditionally just like a version of P, except our algorithms run on different machines, these non-deterministic machines. However, we can talk about it in terms of just regular deterministic machines. So what we do is we're now looking at our output, right? And our output will be of size n. Our input will be of size m, and our algorithm will also run in polynomial time in the time that is polynomial in the size of the input. And if we have this restriction that our input is polynomial in the size of our output, then we have all our outputs are so the sort of union of valid outputs would be in the class NP. It would be some language in the class NP. So it's slightly different to how it was phrased in the input, because the input here was just anything and this output decided it. But here, just everything that can be an output will be in this language, which will be a language in NP. Right, so I mean this is kind of like a little backwards framework, and this can be quite used in some way. So the idea here is that we've got some sort of thing that we want to verify, and we verify it using an algorithm that runs in polynomial time, right? And that's kind of how we can see NP. It's a class of all languages where there is a polynomial size witness that checks it in polynomial time, right? And so we can sort of reword our framework here. So we can think of it as we've got a theorem and we want to prove it. So we've got a proof that runs through a proof checker, which we call a proof system, and outputs the theorem, or tells us that it's not a proof. So here, all we've done is we've taken what we had before, this framework for NP, but now, since we're not just talking about NP things, we just relax the idea of this proof. It doesn't have to be polynomially bounded in the size of the theorem. Okay? And this motivates proof complexity. So proof complexity is now we're studying m's growth in terms of n. So before, m's growth, when n was a theorem in some NP language, m's growth was polynomial, right? Given a good proof system. And we could have like it growing in a different way, right? It could be exponential, it could be double exponential. So now we've just sort of relaxed this framework of what was like NP languages just to any sort of language, and we've got this this idea of a proof here. Okay, and now I'm going to formalize it. Okay, so a proof system, so this is this middle thing here, is a partial function that maps proofs, those were the inputs, to their theorems, which were the outputs. So a proof system for an arbitrary language L over an alphabet gamma. Okay, so gamma here, we're normally going to have gamma to be binary, right? So that means that gamma star is all the binary strings. That's just what this notation means. So F is our proof system. It takes strings to strings. That's quite simple. And a proof system needs to have, so the proof system F needs to have these three properties. First of all, F must be computable in polynomial time. Why do we have this condition? Well, it's the idea that a proof has to be rigorous, right? If it's not computable in polynomial time, that means there are steps in the proof which require very exhaustive checks to be done by the thing checking the proof. In this case, it will be the proof system. So the proof system would have to perhaps run in super polynomial time, or it could be like if you're just reading a proof, you are the proof checker, right? And if you had to make exhaustive checks, you wouldn't really think this is a proof. You'd think this is like a sketch proof, for example. So that's why we have this verifiability property. It is quite nice. It just tells us that proofs need to be easily checkable. Okay, now these two other properties that are also very essential to a proof system, soundness. First of all, we don't prove any theorems that aren't actually theorems. Okay, that's basically what soundness is saying. And it can be written as this, that the range of our proof checking function is within our language. The completeness property tells us that our proof system is doing well. It can be used for anything in our language. So the completeness is the idea that if we've got some theorem in our language, there's going to be a proof in it the proof checker is going to recognize. Okay, and now this is just coming back to what we had before. In terms of proof complexity, a language has a proof system with polynomially bounded proofs if and only if it is in the class NP. This is just exactly what we had here. So now we've got polynomially bounded proofs here, and if we have that, then we're in NP. If we don't have that, we're just in a general proof system. Okay, and this is another way of defining NP, very similar to the way I defined it before, but it's very different from the original definition of NP. Okay, so I'm going to talk a bit about proof simulations. First of all, I'll just mention something about size. So proof size could either be the number of lines or it could be the number of characters. So in a lot of proofs, a lot of proof systems, you have like a system where you've got like a bunch of lines And it's sometimes just more convenient to define proof size that way, and it's usually like equivalent in the sense of like polynomials to like the number of characters, in binary, for example. And now we're going to define this idea of a simulation, or in this case, a P simulation. So we've got two proof systems, F and G. We say that, we want to show that basically F can do anything that G can do. So there's some way of saying F is better than G. And we do that by having some computable function, H, which is polynomially time computable. And what H does is it maps G proofs to F proofs, right? And if you can do that in polynomial time and preserve the theorems as well, then you're basically saying that anything we can do in G, we could do in F, modulo a polynomial. So that's the idea of a P simulation. And P simulations are transitive and antisymmetric and reflexive, so we get a partial order. And from a partial order, we can start doing things like Hasse diagrams. So this Hasse diagram here just tells us what simulates what else. So things above other things are the things that are simulating. So those are like the Fs. So this will be F simulates G, for example. Okay, I'll just talk briefly about these different proof systems. We won't go into any details, but on the top you've got stronger proof systems, and the bottom you've got the weaker, more like proof systems with larger proofs. So like right near the bottom, and this doesn't mean it's necessarily going to be the worst. You could invent even worse proof systems, but out of the common proof systems, you've got the truth table, and the truth table is pretty expensive, right? So what the truth table does is it looks at propositions. You check every assignment, and you check that every assignment gives you a every assignment satisfies the formula, right? And if you check that for every assignment, you've got a tautology. And if you check every assignment returns false, then you've got a contradiction, right? Then we've got these resolution systems. So resolution systems work in a specific conjunctive normal form, propositional formulas, and use just a single rule in order to decide whether it's a contradiction or not. And you can invert contradiction to mean tautology. Okay, so all I'm saying here is that it's just like a proof system that uses one rule. I probably complicated it a bit there. Speaking of complicated, let's talk about these algebraic proof systems. So what are these? Okay, so the idea here is that these proof systems work by taking propositional logic and converting it into algebraic equations using polynomials and using polynomial arithmetic. And this can be used, so say if you have like a set of like a proposition which you know is a contradiction, you can then specify a set of polynomials which have no satisfying values for their free variables, and you can prove that using algebra. So it's using the idea of this proof in algebra to prove things in logic. It's not as complicated as it seems when you actually see these. As well as sort of algebraic equations, you've got algebraic inequalities, linear inequalities, and this happens in this proof system cutting planes, which has an advantage over the resolution system. Right, so these are kind of like messy, complicated techniques, but there are actually simple, just logic techniques, and these are used in these Frege systems. So Frege systems, what they do, you have a bunch of axioms, you have a bunch of rules, and together these are complete for all the operations that you're using. And if you have that, then you've got a Frege system, and these Frege systems are very powerful. They simulate cutting planes, resolution, these polynomial calculi, and they don't have a lower bound. So everything below this line is is not polynomially bounded. We know for sure it's not polynomially bounded because we have families of formulas where we know that the shortest proof must be super polynomial in the size of the theorem. Okay, but for these Frege systems and beyond, so we've got some improvements of Frege systems, we don't know whether it's polynomially bounded or not. So there's a chance it could be polynomially bounded. And if it's polynomially bounded, it means that that the languages that we're looking at, which is a language of tautologies, is in the class NP, which would be huge because it would show that co-NP equals NP. So NP is closed under complementation. This is not what we would expect, right? It wouldn't quite show that P equals NP. Now, a lot of people who've heard P versus NP would know this is like a big Millennium Prize problem. It won't show that. If we showed that Frege was polynomially bounded, it wouldn't be the same as that. Although, and you know, if P equals NP, it doesn't necessarily mean that Frege is polynomially bounded. On top of this, we have the idea of an optimal proof system. Okay, so an optimal proof system would be a proof system that simulates every other proof system. And if NP equals co-NP, then we would get an optimal proof system. And in if P equals co-NP, then we would get a p-optimal proof system where we have p simulations everywhere, rather than just simulations, which is for optimal proof systems. And I didn't mention the difference between p simulation and simulation, but there's another version of simulation which is slightly weaker than p simulation. Okay, so like if we want to talk about p simulations, we'd talk about p-optimal. Right, so we don't know whether there's an optimal proof system, we don't know whether there's a p-optimal proof system. And these are like the open problems in propositional proof complexity here. What I study isn't this. I don't really look at these propositional proof systems. Remember before where I mentioned that you could change the language. So here the language is just like the language of tautologies, propositional tautologies. I specifically look at different logics that are more advanced and have more sort of expressivity, or like can express things more succinctly than propositional logic. So that's specifically what I do, although that now goes beyond the scope of this talk. So I think I'm going to finish here. So thank you very much for listening.